Hello. So today we're going to talk about chapter 3.2, and we're going to talk about our scatter plots and specifically what happens when we have linear scatter plots. And we're going to come up with what's called the least squares regression line, the line that kind of goes through the center of all of our data and best describes the data. So chapter 3.2 is called least squares regression. Here's your learning targets. And we're just going to start with a quick review. So think back to when you took algebra 1. Oops, excuse me. If you had a scatter plot and you were asked to pick a line that best fit the data, what would it look like? So you may have gone through and drawn like your line that kind of goes through the middle of all the points. And it's kind of hard to do this, but you would maybe like draw a line originally. You might have to change like the slope. You might have to change the y-intercept, but eventually, once you draw your line, let's say that this blue line is the line that I draw. If you wanted to write the equation of the line, you would use y equals mx plus b. You would find the slope of the line, and you would find the y-intercept. And keeping in mind, the line doesn't necessarily have to pass through any of the points on the scatter plot. You know, it kind of goes through like this point here and like kind of almost through there, not quite. But it looks like it might go through this one. But that doesn't even matter. It doesn't even have to. Once we, have this line, we're going to write the equation of the line. So the y-intercept, or like the b value, is 3. And let's say the slope goes like up 1 over 2. So the slope looks like it's 1/2. So my equation of the line of best fit would be 1/2 x plus 3, right? We're going to essentially do that today. That's going to be our goal. But you're not really ever going to do this by hand. Your calculator is going to do it for you. So regression. Regression is a method for finding the line that summarizes or approximates the relationship between two quantitative variables. And the regression line is the actual line that you kind of come up with. It models how a response variable y changes and as an explanatory variable x changes. This line is a mathematical model and therefore is going to be used as a predictor. So basically, it's a mathematical model, kind of like what we talked about density curves. It's kind of a summary. It's summarizing the relationship. Now, regression requires an explanatory and response variable. Think about why. Let me go back. Here in this case, I wrote my equation of the line based upon these points being plotted. Like this point, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the point somewhere close to 10, 1, 2, 3, 4, 5. Not exactly, but this is the point close to 10, 5. So the x value is 10, the y value is 5. Now, if I had switched x and y, so if I had plotted, these values on the y-axis and the y values on the x-axis, so this point would be somewhere up here, 2, 3, 4, 5, somewhere like around here instead. And therefore, my whole equation, I would get a completely different equation. All the x's and y's would be flipped. So that's essentially what this third bullet here is saying. With regression, we require an explanatory and response variable. All right, so linear relationships between two quantitative variables are common. So the regression line summarizes the relationship between these two variables, but Again, only in a specific setting, only when we have a clear explanatory variable and a clear response variable, when one variable helps to explain the other. So here's a little example. I have the number of miles driven on a truck and the price that the truck is sold for. I have this data all plotted. And then that blue line is my regression line. Okay, so the equation that you can see here, it's kind of small, but that equation is what we call the regression line or the regression equation. You're going to notice that I have this little symbol. It's kind of hard to see, but it looks like that. And we call this y hat. And in statistics, when we write our regression lines, you're going to notice instead of using like y equals mx plus b, we have this y hat equals a plus bx. So the y-intercept comes first, and then the slope comes second, along with the x variable. So why do we use y hat? It's kind of like the same thing for, why do we use x bar when we talk about the mean as opposed to mu? So x bar indicates that, my data came from a sample. Y hat indicates that my data came from a sample. This is an estimate. That y hat value is an estimate. Or in other words, it's a predicted value of y for a given value of x. All right, so here's the data we were just looking at. If we have a random sample of 16 used Ford F-150 Cruise 4x4s, and this data came off of that website, autotrader.com. The data is shown here. This is the raw data. We have the number of miles driven and then the price that the truck was sold for. So the regression equation is here. Notice y hat, we have that like price hat. It's a predicted value. So the question is asking us to predict the price of a Ford F-150 that has been driven 100,000 miles. So what we can do is we can, looking at the graph, say, oh, here's 100,000 miles. What's this value here? What's this y value? Or in other words, the predicted price. It's kind of hard to estimate that price just from the graph. So instead, we can use the equation. We can plug in $1,000 to the equation and solve for price. So our predicted price is $21,967, right? So the question is, can we predict the price of a Ford F-150 with 300,000 miles driven? So same thing. We're going to plug in that 300,000 miles. So the price is negative $10,613. Let's think about this. If I go back a second to this graph, we're talking about a car that has 300,000 miles driven on it. That's like all the way out here somewhere, maybe, My data, the highest data point is maybe this one, the greatest number of miles driven, right? Is like 144,000 miles. So do I have data around that 300,000 mile mark? Do I have any other cars that gives me any data? No, not even close, right? So it kind of doesn't make sense to use the data that we have to make this prediction. So we call this extrapolation. Extrapolation is when we make a prediction, but way far outside of the interval of x values that we used to obtain the original line or the original equation, right? And these predictions are often not accurate. Things change. Could we still sell a car? Do you think that cars are sold with 300,000 miles on them? I mean, maybe that's a lot of miles, maybe they are. But do we say like, oh, here, I'm going to sell you this car and like, I'm going to pay you to take it. Like, I'm going to give you a negative amount of money. No, that just doesn't make sense, right? So extrapolation is always, always, always dangerous. We should never do it. And in fact, if you're asked to do it, you're going to say, I don't have a lot of confidence in this number, whatever it is, the dollar amount or whatever it is that I'm predicting, because this is extrapolation. And I don't know if this pattern continues. On the other hand, what we call interpolation is predicting y given an x value within the domain of given x value. So that was kind of like when we made that prediction for how much would a car cost that had 100,000 miles on it. That was interpolation, and that's okay. That's good to do. We do that all the time. The whole point of coming up with a regression line is so that we can make a prediction. But you should be careful with extrapolation. In the real world, does it happen? Absolutely. Again, we want to make a prediction, but we don't know if that pattern is going to continue. All right, let's talk about what's called a residuals. So in most cases, it says most, but it's pretty much all. So in almost all cases, no line will pass through exactly all the points in a scatter plot. In other words, no real data is perfectly linear, right? So because we use the line to predict y from x, the prediction errors we make are errors in y, or in other words, the vertical direction in the scatter plot. So this is very important. When we talk about the prediction error, the error that we make, we're talking about in the y direction, right? X is given to us. Our error is in the prediction that we make. So we're going to call those vertical distances residuals, or in other words, it's kind of like the leftover variation in the response variable y. So going back to that data that we were just looking at before, if I have, that blue regression line, the red dots are the actual data points. Again, here's your equation, y hat, because it's a prediction, right? So like this red data point, the distance in the y direction from that data point to the line is what we call the residual. So some of our residuals are going to be, bigger, and some are going to be smaller because some of the points are going to be really close to the line. So how do we calculate an actual residual? So to calculate the residual, we're going to take the actual y value. So that would be like this value here, and we're going to subtract the predicted y value. So that would be the y value along that blue line. So in other words, we take y minus y hat. So you might be able to tell that some of our residuals are going to be positive because the actual y is above the predicted y. But some of the residuals might be negative because the actual y is below the predicted y. Or in other words, below the regression line. So same data set that we've been looking at, we're going to calculate this question down here. We're going to calculate and interpret the residual for the truck that was driven 70,583 miles. So that's this truck right here. So first we need the regression line, or the regression equation, which we have, right? And we're going to find the predicted price. So we're going to plug in the number of miles driven, and we're going to come up with the predicted price, right? Then we're going to look at the actual price that it was sold for, and we're going to subtract the actual price minus the predicted price. So price minus price hat, y minus y hat. And you can see that the predicted price was higher than the actual price that it was sold for, so your residual is going to be negative. In other words, if I were to look at that point on the regression line, on the scatter plot compared to the regression line, it would be below the regression line. Now we're going to interpret that residual. So your interpretation was that the actual price of the truck was $4,765 less than the cost that was predicted by the regression line, right? You're going to be asked a lot to interpret residuals. and your interpretation always has to be kind of similar to this. In context, specifically talking about if it's less than or greater than, depending on if the residual is positive or negative. All right, so like we said in the very beginning, a regression line is a model for the data, much like the density curves of chapter 2, right? So the y-intercept and the slope describe what the model tells us about the relationship. It kind of summarizes the relationship between x and y. So in the regression equation, y hat equals a plus bx, a is the y-intercept. So comparing this to like y equals mx plus b, and this is a little bit confusing because in algebra we learn like y equals mx plus b, and we say, oh, b is the y-intercept, right? And m is the slope. So in statistics, for whatever reason, statisticians reverse these, and they use b to represent the slope and a to represent the y-intercept. So a is the y-intercept, and remember, the y-intercept from algebra is like where x equals 0. So it's the predicted value of y when x equals 0. And you're going to be asked to interpret the y-intercept and interpret the slope. And so you got to remember that this is what's happening. What are we predicting to happen when x equals 0? Well, here's the thing. This is like real life data. So sometimes x can't be equal to 0. You know, for example, if I'm talking about like the newborn babies, if I'm looking at the length of a newborn baby versus their weight, saying that the length of the baby is the explanatory variable and the weight is the response variable, you know, I could plot my data and let's say I have like 100 babies, their lengths versus their weights, right? And I mean, I don't know for sure, but I would assume that they probably have like a positive relationship. As the length goes up, the weight also goes up as well. And I could come up with a regression equation. But whatever my y-intercept is, would it have meaning? The interpretation of it would be when the length of the baby is 0 inches, the weight would be whatever. That doesn't make sense because I can't have a baby that's 0 inches, right? So this is what we mean when we say this. The value is only useful if the regression has meaning near x equals 0. On the other hand, b is the slope, the amount by which the predicted or average value of y changes when x increases by 1 unit. So this is also going to be important. You know that like slope is rise over run, right? Or in other words, like the change in y over the change in x, like y2 minus y1 over x2 minus x1. Remember all these formulas. So our y values here are what we predict, right? So it's what the predicted value of y change is going to be when x increases by 1. So the x is changing as well, increasing by 1, right? And our predicted y value, if our slope is positive, we predict that y is increasing as x is going up by 1. If our slope is negative, we're predicting that the y is decreasing as x is going up by 1. All right, so let's practice this a little bit here. Same idea. We're going to interpret the slope, and then we're going to talk about the y-intercept as well. So the slope of the regression line right here, right? And it's negative. So that tells us that the predicted price of a used F-150 goes down by 0.1629 cents for each additional mile that the truck has been driven. So let's pick out a couple important things. First of all, we're using the predicted, that word predicted, or the average. You have to have that word in there. It's in context. We're talking about it going down because the slope was negative, right? And then we're talking about the y value going down for each one additional mile that the truck has been driven, right? The change in y divided by the change in x. Okay, part B, Does the value of the y-intercept have meaning in this context? If so, interpret the y-intercept. If not, explain why. So there's our y-intercept in purple there, that 38,000 number. So again, we're talking about where x equals 0. So x here is the number of miles that have been driven. So could we have a Ford F-150 that has no miles on it? Absolutely, when it's like brand new, right? So the y-intercept tells us about the predicted price of the Ford F-150 that has been driven 0 miles. All right. So again, make sure we're talking about the predicted value, right? Okay, so you can use the regression line, the slope of the line specifically, to talk about the nature of the relationship between your explanatory and response variable. In other words, as x is increasing by 1, how much is y changing, increasing or decreasing? But to talk about how important or how strong the relationship is, the slope doesn't tell us how strong it is. Our R value tells us that, right? So the slope, I could have, 2 variables, and the slope between the two could be like 1,000,000. Or I could have another 2 variables, and the slope between the two could be 5. That doesn't mean that the first one had a stronger relationship because it has a bigger slope, right? In order to tell me how strong or how important the relationship is, we need R. And you can kind of read a little summary a little bit more in your book on page 182 if you're interested. Okay, so now that we know a little bit about regression, let's talk specifically about what's called the least squares regression line. So there's many different lines that we could use to model the association in a particular scatter plot. A good regression line makes residuals as small as possible. So we want a regression line that makes those residuals small, right? And the smaller the residuals, the better the line. So the regression line that we're going to call as like the best one minimizes the sum of the squared residuals. And let's talk about why. So here's the same data, right? Remember, ignore these blue squares for a second. Let's just talk about these black residuals. Some of these residuals are going to be negative. Some of them are going to be positive. So here's the thing. If I, have, let's say, this blue line versus, let's say, like this red line, right? How do I know which one is better? Well, I want the residuals to be as small as possible. Well, if I add up all the residuals, that's not going to tell me much because some of the residuals are going to be negative, some are going to be positive. And so they're going to kind of cancel each other out, right? So instead of adding up the residuals, we're going to square each of the residuals and then add up those values. And then we want to minimize the sum of all the squared residuals. So if this residual is 5, if we have a residual that's 5 versus one that's negative 5, instead of adding them together and saying, our sum of the residuals is 0, no, we would take the 5 and square it, 25, the other negative 5 and square it, still 25, and add them up and say the sum of the squared residuals is 50, right? So the sum of these squared residuals is that big number. But we want to minimize those. So what we call the least square regression line, or in other words, LSRL. We're going to be using that notation, and you can use that abbreviation as well. That's kind of like an understood abbreviation. So the LSRL, least squares regression line, is the specific line that makes all the sum of all the squared residuals as small as possible. And so you're never going to have to, there's a process that you could go through to do this by hand, but it's, very difficult, lengthy, so you're never going to actually do it. you're either going to be given the equation of the LSRL, y hat equals whatever, or you can put raw data into your calculator and you can use, you have like the X values in L1, the Y values in L2 or L3 and L4, whatever, it doesn't matter which list. And then you're going to use the function on the calculator. We've already used this function to find our R value. And so we're going to use the same function, statcalc linreg. And there's two linregs. You could use, I think it's ax plus b, or I think it's linreg a plus bx. Either one is fine. But then that's going to give you the least squares regression line, the values for, the slope and the y-intercept. And then just a fun fact, let's call it, and we'll talk more about like why do we, or why or how do we use this, but every single least squares regression line, so specifically the least squares regression line, the one that minimizes the sum of the squared residuals, every single LSRL for every set of data is always going to pass through this point, x bar comma y bar. So let's take a second, break this down. When I say x bar, y bar, what I mean is I would take all of these points, all of these red points, and I would calculate, I would just look at the x values. So just the x values, just the number of miles driven. I'm going to ignore price. If I find just the number of miles driven and take the mean of all of those miles, and then I just look at all the prices. Again, now I'm ignoring the miles driven, so just the prices. And if I calculate the mean of all the prices, and I put those two values together, so the mean of all the miles, the mean of all the prices, that x bar y value, x bar y bar value is going to be somewhere on this line. Exactly, it will be a point exactly on that LSRL line. I don't know exactly where, but somewhere. Okay, that is all I have for you. Thank you so much for watching. Please email me if you have any questions. Have a great day.